afternoon, everyone. I'm Divya Jain from the Department of Computer Science and Engineering at Acropolis Institute of Technology and Research, Indore. Today I'll be presenting on video file formats, specifically MPEG and its family of standards. MPEG, which stands for the Moving Picture Experts Group, was founded in 1988. In just a few decades, it has shaped how billions of people around the world watch, store, and stream video. So let's dive in. Table of content. Here's a quick overview of what we'll cover today. We'll start with the basics of video formats and MPEG, trace its history, then go deep into each major standard, MPEG-1, MPEG-2, MPEG-4, MPEG-7, and MPEG-21. We'll also cover the technical concepts that make compression possible, DCT, IPB frames, and wrap up with a comparison and real-world applications. Video file formats. Before we talk about MPEG specifically, let's understand what a video file format actually is. A video file format is essentially a container. It holds video data, audio, subtitles, and metadata together in one structured file. Think of it like a shipping box. The box doesn't matter as much as what's inside, but the box determines how everything is packed and how easily it can be opened. Formats matter for 4 key reasons. Storage. Compressed formats can save gigabytes of space. Streaming. Optimized byte rates ensure smooth playback online. Quality. It's about balancing resolution with file size. Compatibility. Different devices and platforms support different formats. What is MPEG? MPEG stands for Moving Picture Experts Group. It's a working group under ISO IEC that develops international standards for audio, video, and multimedia compression. It was co-founded in 1988 by Hiroshi Yasuda from NTT Japan and Leonardo Chiariglioni from CSELT Italy. Over the decades, MPEG has produced a whole family of standards, each identified by an ISO number. You can see them here: MPEG-1, MPEG-2, MPEG-4 for video and audio encoding, MPEG-7 for content description, MPEG-21 for digital rights and delivery frameworks. Each of these serves a different purpose, and we'll explore them one by one. History and evolution of MPEG. Let's look at the timeline. MPEG was founded in 1988. By 1992, MPEG-1 was published. It was designed for VCD quality video on CD-ROMs. In 1994, MPEG-2 arrived, bringing DVD and digital TV quality. This is still widely used in broadcasting today. 1999 saw MPEG-4, designed for the internet and mobile devices, and it introduced the H.264 codec, which revolutionized streaming. Then in 2001, MPEG-7 came along, not for encoding, but for describing multimedia content. Later milestones include MPEG-21 in 2002 for digital rights management, and MPEG-5 in 2020 with the essential video coding standard for next-generation efficiency. Each standard was a response to the technology and bandwidth of its era. Standard. MPEG-1, published in 1992 under ISO IEC 11172, was the first practical digital video standard for consumer use. It has 5 parts: systems, video, audio, conformance testing, and reference software. Key specs. It supports a resolution of up to 352 times 240, called SIF or source input format, at up to 30 frames per second, with a maximum bit rate of 1.5 megabits per second, just right for a CD-ROM. It achieves approximately 26 1 video compression using the YCBCR4 2 0 color space. Its primary application was the video CD, VCD, which many of you may have seen in the late 90s. It was also used for early internet video and CD-ROM multimedia. Layer 3, MP3. Now, arguably the most famous outcome of MPEG-1 is not the video standard, it's the audio. Specifically, MPEG-1 audio layer 3, better known as MP3. MPEG-1 defined 3 audio layers. Layer I has 4:1 compression, layer 2 has 8:1, and layer 3, MP3, achieves 12:1 compression with the best quality. How does it do this? MP3 uses a psychoacoustic model. It removes sounds that the human ear cannot actually perceive, especially at high frequencies. The result, 90% smaller files than uncompressed audio, while maintaining near CD quality. MP3 enabled portable music players like the iPod and Walkman, and made music streaming possible. PEG to standard. Moving on to MPEG-2, published in 1994 under ISO IEC 13818. This was a massive leap from MPEG-1. Where MPEG-1 supported only 352 times 240, MPEG-2 supports up to 1920 times 1080, full HD TV resolution. The bit rate range jumps from 1.5 megabits per second all the way to 80 megabits per second. MPEG-2 introduces profiles and levels to define combinations of features and resolutions. This allows the same standard to serve everything from standard definition TV to high definition broadcasts. MPEG to transport and program streams. MPEG-2 also defines 2 types of bitstream containers. The transport stream uses fixed 188-byte packets and is designed for lossy transmission environments like broadcast. It handles multiple programs in one stream, with error resilience and PCR timestamps. This is used in DVB and ATSC broadcasting. The program stream uses variable length packets, is designed for reliable storage media like DVDs and Blu-ray, and carries a single program per stream with lower overhead. This distinction is why you see .ts files in broadcast recordings and .warp files on a DVD. MPEG-4 standard. MPEG-4, published in 1998-99 under ISO IEC 14496, was a paradigm shift. It was designed for low bitrate internet streaming, mobile media, and interactivity. Its most groundbreaking idea was object-based coding. Instead of encoding a scene as a whole picture, MPEG-4 encodes individual objects, video, audio, text, and 2D, 3D graphics as separate, independent objects. This allows selective manipulation of content. Key parts include Part 2 for visual coding, Part 3 for AAC audio, better quality than MP3 at the same bitrate, Part 10. This is H.264 AVC, the most widely deployed video codec in the world, Part 14, the MP4 file format that you use every day on your phone. It also MPEG-4 Part 10, H.264 AVC. Let's spend a moment on H.264, also called AVC, Advanced Video Coding, because it is arguably the single most impactful video codec ever created. H.264 is used in Blu-ray, YouTube, Netflix, smartphones, and virtually all video conferencing platforms. It defines multiple profiles for different use cases. Baseline, for mobile and video conferencing. Main, for standard definition TV. High, for HD streaming and Blu-ray. High 4, for professional production. The most remarkable thing about H.264 is its compression efficiency. Compared to MPEG-2, H.264 reduces the required byte rate by approximately 60% for the same visual quality. That's why HD video streaming became practical. It halved the bandwidth requirements. MPEG-7 standard now. MPEG-7 is fundamentally different from everything we've discussed so far. Previous standards were about encoding content. MPEG-7, published in 2001, is about describing content. It's called the Multimedia Content Description Interface. It defines descriptors for low-level features like color, texture, and shape, descriptor schemas for how they relate, a DDL, and XML-based language to define descriptions, and a description header for metadata. Applications include image search engines, digital libraries, and broadcast monitoring. Think of Google reverse image search. The principles behind it are very similar to MPEG-7. MPEG-21 and other standards. MPEG-21, published in 2002, is a multimedia framework for delivering and consuming media across networks and devices. Its core concept is the digital item, a structured digital object with associated rights and metadata. It handles device adaptation, IP management, and usage rights. Beyond this, MPEGA in 2007 covers multimedia application formats. MPEGV in 2011 handles virtual world interaction, and MPEG-5 in 2020 introduces essential video coding, high efficiency at lower computational cost for next generation DCT and encoding. Let's look at how MPEG actually compresses video. The core tool is the discrete cosine transform, or DCT. An image is divided into 8 times 8 pixel blocks. DCT converts each block from the spatial domain into the frequency domain. Low-frequency coefficients represent broad visual content our eyes are sensitive to. High-frequency coefficients, fine detail we barely notice, are quantized heavily and discarded. The full encoding pipeline goes: color space conversion, block partitioning, DCT quantization, entropy coding, bitstream output. iframe, bframe, and GOP. DCT handles compression within a single frame. But consecutive frames in a video are often very similar. MPEG exploits this with 3 frame types. Iframes are complete standalone images. Largest in size, but they're the key frames used for random access. P-frames store only the difference from the previous frame using motion vectors, much smaller than iframes. P-frames reference both past and future frames, achieving the smallest size and best compression, but they can't be decoded independently. A group of pictures, or GOP, is the repeating sequence of these frames, typically I, B, B, P, B, B. Bitrate, resolution, and video quality. Video quality is measured through a few key metrics. PSNR measures pixel level accuracy. SIM measures perceptual quality, closer to how humans actually see differences. MOS is a subjective score gathered from real viewers. Bitrate is the data per second. Higher means better quality but larger files. CRF, or constant rate factor, targets a consistent quality level rather than a fixed bitrate. MPEG standards comparison. Looking at this table across all major standards, MPEG-1 from 1992 supports only 352 times 240 at 1.5 megabits per second. Legacy today but foundational. MPEG-2 from 1994 reaches 1920 times 1080 at up to 80 megabits per second, still active in broadcasting. MPEG-4 from 1998 supports up to 4K across a huge bitrate range, used everywhere from internet to mobile. MPEG-7 and 21 have no resolution or bitrate. They're metadata and framework standards. MPEG-5, the newest, supports up to 8K for next-generation streaming. Compression efficiency across standards. This chart shows how efficiency has improved across generations, each standard delivering better quality at the same bitrate. This progression is precisely what makes 4K streaming on a home connection possible today. MPEG versus other video formats. Comparing MPEG against other formats. MPEG 4 with H.264 scores highest on compression, quality, compatibility, and streaming. It's the gold standard for modern delivery. AV scores well for editing but poorly on compression and DRM. MKV offers great flexibility but uneven device compatibility. MOV performs well overall but has limited cross-platform openness. Advantages and limitations of MPEG. On the advantages side, MPEG standards are internationally recognized, ensuring interoperability across billions of devices. Compression ratios are excellent, and the standards scale from 240p all the way to 8K. On the limitations side, MPEG uses lossy compression. Original data cannot be perfectly recovered. H.264 carries patent licensing fees. B-frames add latency in real-time applications. And despite strong capabilities, MPEG 7 and MPEG 21 have seen limited industry adoption. Before I close, here are the 6 things I want you to remember. 1. MPEG is a family of standards, each targeting a different use case. 2. Compression works through DCT for spatial redundancy and IPB frames for temporal redundancy. 3. MPEG remains the backbone of global broadcasting. 4. H.264 dominates streaming, powering over 65% of online video. 5. MPEG 7 describes content rather than encoding it, enabling intelligent search. 6. The future is MPEG 5 and H.265, offering 40–50% better compression than H.264 for 4K and 8K. Thank you, and that brings me to the end of my presentation. MPEG started as a solution to a simple problem. How do you store and transmit video efficiently? In answering that, it created the infrastructure behind every DVD, every broadcast, every YouTube video, and every video call we make today. Thank you for your time and attention.